Welcome all. Welcome to this particular lecture of combinational circuits part 4. In this lecture, we will discuss about the code converters and magnitude comparator. So what is a code converter? Code converter is a logic circuit that changes data presented in one type of binary code to another type of binary code, such as BCD or binary coded decimal to binary, BCD to 7 segment, binary to gray code, and gray code to binary. Now we will see what are these codes actually and how we can convert from one type of code to another. So first we will see the 4-bit binary to gray code. What is gray code? So the gray code belongs to a class of codes called minimum change codes, in which only one bit in the code group changes when moving from one step to the next. Okay, the gray code is a non-weighted code, therefore it is not suitable for arithmetic operation but finds applications in input output devices and some type of analog to digital converters. Okay, so first let us see the operation, how to convert a binary code to the gray code. Suppose I have this number in binary 1 0 1 sorry, let me cut this. The binary code is 1 0 1 1 0. So now how we will convert this binary code to the gray code? So the first bit MSB of the gray code is same as the first bit of the binary number. That means this MSB one we will write as it is. Then what we will do? We will perform then the XOR operation between this first MSB bit to the second bit. 1 0, if we perform the XOR, what we will get? We will get 1, right? Then what we will do? Second bit and third bit, we will perform the XOR operation. So 0 and 1, if we do the XOR operation, we will get 1, right? Then if we perform the XOR operation between 1 and 1, that means between the third bit to the fourth bit, what we will get? We will get 0. If the number is same, we get 0 in XOR, right? And if we perform the XOR with this 1 and 0, we will get 1. So this is my binary code and this is the equivalent gray code. Okay. So for each binary digit, what we have to do? First, we have to write all the numbers, all the binary numbers starting from 0 to 15. Okay, that means 0 to 15, they are the decimal numbers and we have to write the corresponding binary numbers, right? 0 0 is 4-bit binary numbers. Since it is a 4-bit number, we have to write this is 0 0 0 0 0 0 0 0 1 0 0 1 0, like that. Okay, till 15, 1 1 1 1. Now for each binary digit, we have to use this operation. Okay, so this is the forum. I have taken a 5-bit binary number. So for this 5-bit binary number, I have performed the gray code operation. So for each binary digit, each binary bit, we can perform the gray code operation like this. First MSB we have to write as it is, and for the second digit we have to perform the XOR operation between the first and the second, then second and third, then third and fourth, then fourth and fifth. Okay, so we will get all starting from 0 0 0 to 1 1 1 1. So for all these numbers we will get the gray code equivalent. Okay. Now this is my binary input B4, B3, B2, B1. B1 is the LSB of that binary number and B4 is the MSB of that binary number. And this is the corresponding gray code output where G1 is the LSB and G4 is the MSB. Now for each output column, this is my input, right? And this is my output. So for each output column, we have to check where we are getting the 1. For the G4, we are getting 1 starting from 8 to 15. So we have to perform for each G4, G3, G2 and G1, we have to perform the Carnot map. Okay, that means we need to get the simplified Boolean expression. So how many inputs are there? Total 4 inputs. So total 16 cells we will be there. First we have to number the cells. This is, let's say, B4, B3 and this is my B2, B1, right? So after that what we will do if we are doing for G4, so all the cells starting from 8 to 15 we have to number 1 and see we can perform this box. We can perform this Carnot map operation and it is all the ones we can cover and it is covering 8 cells. So what will be my output for this particular? Here which one is not changing? B4 is not changing. So B4 will be my Carnot map for this G4. Next, if you see the G3 starting from 4 to this is 9, this is 8, 9, this is 10, 11. So till 11 all the starting from 4 till 11 all are 1. 4, 5, 6, 7, 8, 9, 10, 11 all are 1. So this for this entire row we will be having B4 bar B3 plus for this entire row we will have B4 B3 bar. This is nothing but the XOR between B4 and B3, right? So G3 will be B4 XOR B3, right? So next you see the G2. Okay, see the columns for which this G2 value is 1. Take that combination. Okay, now G2 is 1 for 2, 3, then 4, then 5, then again here you come for 10, 11, 12, 13. So for those corresponding cells, we have to fill with 1. So now we will perform the Carnot map operation. So this and this, we will perform the Carnot map operation. Okay. So it is G2 is giving me B3 XOR B2. Okay. Now for this G1, those corresponding, we will see for which input combination G1 is 1. So those cells we have to fill it with 1. Okay. So G1 is 1 for 1, 2, here I can see it is 5, 6, then 9, then 10, then again 13 and 14. So corresponding those cells, in those particular cells we have to fill it with 1. So for these entire column we will get, this one is B2 bar B1 and this is B2 B1 bar. This is nothing but the XOR operation between B1 and B2. Now all these outputs that we got, G4, G3, G2 and G1, we will express it in terms of the logic gates. Okay. So G4 means what? G4 means it's simply B4. Just first draw 4 input lines, B4, B3, B2, B1. Okay. B1 is my B1 is my LSB and B4 is my MSB. Okay. So G4 is simply B4. What is my G3? B4 XOR B3. So it is B4 and B3. We have to put a XOR gate here. What is G2? It is XOR between B3 and B2. So between B3 and B2 we have to put a XOR gate. That will give us the G2, right? Then for G1 we have XOR between B2 and B1. So between B2 and B1, we have to put a XOR gate. So this is my final logic diagram. So first, what we have to do for code converters, 4-bit binary to gray code converter. First, we have to write starting from 0 to 15. First, we have to write the truth table from 0 to 15, the corresponding binary expressions. Okay. Then for each 4-bit binary, we have to convert to the gray code. Okay. Then we have to see each output column that are 1, we have to see the corresponding input combinations. Then we have to perform the Carnot map operation. Okay. So for which, suppose for G4, we have to see for which input combination this G4 is 1. So those input combinations we have to perform the Carnot map. For those input combinations, we have to number the cells. Okay. That means here G4 is 1 starting from 8 to 15. So starting from 8 to 15, all the cells we have to put 1. Likewise for G3, G2 and G1. Once the Carnot map is done, once we get the Carnot map for each and every G4, G3, G2 and G1, we will simply express it in terms of the logic diagram. Okay. So since there are 16 possible combinations of 4-bit binary input and all of them are valid, hence we don't cares, right? Next we will see the 4-bit gray to binary code converter. How we will perform the 4-bit gray to binary code converter? If you want, you can interchange the table also, because last table we know this one, right? It is, we just have converted binary to gray, right? So now previously my binary was input and gray was output. Now my gray is input and binary is output. Okay. So either you can convert the, first you write the binary codes starting from 0 to 15 and you perform the binary to gray code conversion. You can also perform the gray to binary code conversion. Previous slide I have shown you how to convert this binary number to binary code to gray code. Now I will show you how to perform the gray to binary conversion. So let's say, let's take a digit 1 0 1 1. So this is a gray code. I need to convert this gray code to binary. How I will do? First, these MSB you write as it is 1. Then these 1 and these 0, we have to perform the XOR operation. 1 and 0 XOR means 1 and 0 XOR means 1 and 0 XOR is 1, right? Again, these 1 and this 1, we will perform the XOR operation. 1 1 XOR means 0, right? Then these 0 and these 1, I will perform the XOR operation. 1 0 XOR means 1. So this is my gray code and this is my corresponding binary code. So similar process. This is the gray to binary conversion. Okay. But previously the process was different. Binary to gray code conversion process is different than conversion of gray to binary. So if you have the truth table once you have converted all this binary code to the gray code, you can simply interchange the position of the gray and binary code. Okay. So now gray code is my input and binary code is my output, right? So you can see there are 16 possible combinations of 4-bit gray input and all of them are valid. So don't care. Okay. So the 4-bit input gray code and the corresponding output binary numbers are shown in this figure. Okay. So now we have to check same process like the last time. For this B4, for this B4, the 1 we have to check, 1 is for which input combinations? 1 is from here to here. 1 is from here to here. Okay. So, this is 1100, 1101, then 1111, 1110, 1010. We know, right, the corresponding decimal numbers for this. What is 1100? What is 1000? First tell me what is 1000. 8. This is 9. This is 8, 9. Right? Then 8 is 1000. 9 is 1001. Right? Then 10 is 1010. Like that, for all these input 1 combinations, we have, for all these output 1 combinations of this particular B4, we have to check the binary code. Now, corresponding decimal number we can easily identify. This is 1000. This is 1000 means 8. 1001 means 9. So, all these, wherever we have 1 and corresponding input combinations, we have to notice, and in the Carnot map, those particular cells we have to put 1. Okay. So this is 8 will be 1, 9 will be 1, then this 1010, 10 will be 1, 11 will be 1, like that. Okay. So all I can see here, 8, 9, 10, 11, 12, 13, 14, 15, all are 1 for this B4. So we can easily do the Carnot map. So for these B4, which one is not changing? G4 is not changing. So it will be G4. Next you come to B3. Just see wherever we are getting 1, the corresponding input combinations we have to notice. Okay. So this one belongs to 0, 1, 1, 0. That means 6. This is 7. So this is 5. This is 4. Like that. Then also we have 8, 9 and 10 and 11. So B3 is 1 for this particular numbers. Okay, input numbers. So we have to put 1 in the cells, those particular cells. So for this one, B3 will be G4 bar G3, and this is G4 G3 bar. This is nothing but the XOR between G4 and G3. Now again you come to B2, check the ones, only check the ones where you are getting the ones. Okay, so you are getting ones for here 2, 3, 4, 5, then 8, 9 and 14 and 15. So those particular cells you put 1 and you perform the Carnot map operation. Okay, next again you notice the B1. So for B1 you just check the 1 for which input combination you are getting 1. You are getting 1 for 1, 2, then 4, 7, 8, 11, 13, 14. For these input combinations you are getting 1 for B1 output. So for those particular cells you put 1. So you will get the Carnot map like this. It is a Carnot map between this G4 XOR G3 XOR G2 XOR G1. It's a bit complicated because here once we can't group here. Okay. So once you simplify, you will get this expression for this B1. Now we already got the K map for each and every B4, B3, B2 and B1. So what we have to do now? We will input side, we will put the numbers. G4 is my MSB, G1 is my LSB. Okay, now we are doing the gray to binary conversion. So gray is my input and this is my output, right? So B4 means simply G4. B3 means XOR between G4 and G3. G4 and G3 XOR. Put an XOR gate between G4 and G3. Then B2 is XOR between G4, G3 and G2. So G3, G2 and this B2 will be XOR between G4, G3 and G2. So this is the G4, G3 XOR. So it goes 1 input and G2. Just perform the XOR operation. Now what is B1? It is B1 is the XOR between G1 and take all this. This is the XOR between the G2, G3 and G4. So this is the final logic diagram. Okay. Now we will see 4-bit binary to BCD converter. What is BCD? BCD stands for binary coded decimal, where each decimal digit is converted into its equivalent binary number. This means the LSB and the other significant bits of a decimal number are each represented by the corresponding binary number. Okay. Suppose you have a decimal number 14. Okay. Suppose you have a decimal number 14. This is the decimal number 14. So 1 means what? 1 means 0, 0, 0, 1, and 4 means 0, 1, 0, 0. So this is the BCD representation of the decimal number 14. Okay. Now what we are doing here, see here 4-bit binary to BCD converter. That means input side we will be having the binary and output side we will be having the BCD. So first your job is to write all the decimal numbers 0 to 15. Then you write the 4-bit binary representation of all these 0 to 15 decimal numbers. We know 0000 to 1111. It is very easy. Okay. Then BCD output. How we will write? Okay. See here, the input is a 4-bit binary number. Okay. And there are 16 possible combinations of 4-bit binary inputs. Okay. And all the 0 to 15 are valid. Okay. So no don't cares are there. Since the input is 4 bits, that means a maximum of 2 decimal digits, right? The output has to be an 8-bit one. But since the first 3 bits will all be 0 for all the combinations of inputs, the output can be treated as a 5-bit one. That is why you are observing here in the BCD output, we have represented it as a 5-bit number. Okay. That is why we have represented it as a 5-bit number. You can see in the BCD output starting from the 0 to 9, all starting from the 0 to 9, you can see if you notice this A, the MSB part of these output starting from 0 to 9 all are 0. Just don't consider this A column first. Okay, if you look at this B, C, D, E, you can see all are same starting from 0, 0, 0 to, if you notice here, this BCD output, it is, first you see the A column. In the A column, what we can see here? In the A column, see, in the A column, I have shown you right now how to convert a decimal number to the BCD number, right? 14 means 1 is 0001 and 4 is 0100. So if you notice here, starting from 0 to 9, starting from 0 to 9, all are 0. Okay, and from, I'm only telling for this A, MSB of your output, and starting from 10 to 15 all are 1. Okay, all are 1. So obviously if you have 15, how will you represent it? If you have 15, suppose if you have 15, how will you represent it? You have a binary number 15, sorry, decimal number 15. How will you represent it? This is 0, 0, 0, 1, right? and 15 is 0, 1, 0, 1, right? So what we are getting here? Aren't we getting 10101? This is 10101, right? Because we have to represent it in a 5-bit number. Because as I told you, the input is 4 bits, right? A maximum of 2 decimal digits. The output has to be an 8-bit one. But since the first 3 bits will all be a 0 for all the combinations of inputs, the output can be treated as a 5-bit one. If you take for 14, see here, it is 10100. 10100. If you convert for 13, what you will get? 13 means 0001. This 1 we have to represent it as a 4-bit binary number. Then 3 we have to represent it as a 4-bit binary number. So what you are getting? Are you getting this one? 10011. See here, 10011. Likewise, we have to do it for all these input. We have to convert to the BCD output. Now the process is same. Now what you are doing, if you are representing it in terms of a block diagram, input is your 4-bit binary number, B4, B3, B2, B1. B1 is your LSB and B4 is your MSB, and output you are getting a 5-bit output. Okay, now you just notice all these numbers. Okay, A is 1 starting from this 10 to 15. So starting from this 10 to 15, we have to perform the Carnot map, right? So all these 10 to 15 cells, you fill it with 1 and you perform the Carnot map operation. So for this one, for this entire row, we have B4, B3, and for these 4 cells, what we will have here, which one is not changing? B4, and here which one is not changing? B2. So it is B4, B2. Now you notice the B2 cell, for which input we have the 1, we have 1 for 8 and 9. So 8 and 9 we will put the 1. So Carnot map we will get as B4, B3 bar and B4, B3 bar, B2 bar. Okay. Now, because this is B4, B3 bar and here which one is not changing? B2 bar is not changing. Similarly, for a C column, we have to check wherever we are getting 1, those input combinations we have to take. So, this is your Carnot map. This is the entire, for entire row you are getting B4 bar, B3, and for this entire 4 cells you are getting here which one is not changing? B3 is not changing, and here your B2 is not changing. Okay. So next you see the D column, for which input combination you are getting 1. So those cells you number it with 1. So this is how your Carnot map expression will look like for D, and for E also you check the combinations. You check wherever you are getting 1. So those corresponding inputs you have to take, and this is your Carnot map for E. Okay, now we all know what we have to do. You just draw the input side lines. B4 starting top you put B4, then B3, then B2, B1. Here I haven't shown the logic diagram, that you have to draw by yourself. So you know all the K-map expression for the output, right? Now similar to the previous case, you just draw the 4 digits starting from there in MSB to LSB. Then with the help of the logic gates, you have to get the final output come. Okay, so this is, once you are trying to get A, what you will do, you have to take the, you have to perform the AND operation between B4, B3, then you have to perform the AND operation between B4, B2, and then you have to perform an OR operation between the first term and second term. Likewise, for each and every K-map, we will get the output. Okay. Now, what is magnitude converter? Next, our topic of discussion is magnitude converter. So, 2-bit, when 2 binary numbers are equal, if and only if their corresponding bits coincide. Two binary numbers, we will consider them are equal when, if and only if all their corresponding bits coincide. For example, if you take two 4-bit binary numbers A3, A2, A1, A0 and B3, B2, B1, B0, if they are equal, they will be equal if and only if A3 equals to B3, if A2 equals to B2, if A1 equals to B1 and if A0 equals to B0. Thus, the equality holds when A3 coincides with B3. Equality, here we are using one more term which is called coincides. A2 coincides with B2. A1 coincides with B1 and A0 coincides with B0. Okay. Now, this coinciding we are treating as an XNOR operation. Why? Because the XNOR gate, which is also known as a coinciding gate, is a basic comparator. Okay, because its output, the XNOR gate, what will be the output? The output of the XNOR gate will be 1 only if the two input bits are equal, right? It is a complete opposite to the XOR gate. That means the output is 1 for XNOR if and only if the input bits coincide. That is why we are representing this equality condition as A3 XNOR B3 into A2 XNOR B2 into A1 XNOR B1 into A0 XNOR B0. Okay, it is straightforward, and it is obviously it is obvious that this circuit can be expanded or compressed to accommodate binary numbers with any other number of bits. Okay, so this is 1-bit comparator. You have the two inputs A and B. If A and B are equal, then you will get this E output. If A less than B, then we have this L output, and if A greater than B, we have to consider this G output. Now, let's analyze this condition. Okay, the logic for 1-bit magnitude comparator, let the 1-bit numbers be A and B. Okay, where A is A0 and B is B0. Okay, if A0 is 1 and B0 is 0, that means A greater than B, right? Because 1 is greater than 0, right? Therefore, A greater than B. Okay, so in this case, if A greater than B, so in this, if we consider this logic, my output will be A0, B0 bar, right? Because we have considered A0 1, B0 0. If A0 0 and B0 1, then A less than B, obviously 0 less than 1. So if you consider this logic is your output, so in this case L will be A0 bar into B0. Okay, then if A0 and B0 coincide, that means if A0, B0 both are 0 or A0, B0 both are 1, then A equals to B. And this coinciding condition we have learned that we have to express in terms of NOT gate. And this output we will call as equality output. Equality equals to A0, X0, B0. So if you express this logic in terms of a truth table, this is A0, B0. So with two variables, we can have 4 combinations, 4 input combinations, 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 means both are equal, both A and B are equal, right? So here we have written 3 output, L, E and G. So when 0, 0 is equal, then equality E will be 1, the less than and greater than output will be 0. Now if A0, 0, B0, 1, that means A0 is less than B, A less than B. That is why for the less than output we have written 1, rest of the output will be 0. Now if A0 1, B0 0 means A0 is greater than B0, so for greater than we have written 1, rest of them will be 0. If both A0 and B0 1, then again equality output will give us 1, rest of them will be 0. Now same In the input side, you write two inputs A0, B0. Output side, we'll have three outputs L, E and G. Now for each column, we have to check where we are getting 1 and we have to express it in terms of the logic gate. This L is 1 for A0 bar, B0. So you perform the AND operation between A0 bar. This is A0 bar. Just for a bar, we have used a NOT gate and this is the B0. So AND operation between them. Then E is 1 for A00, B00, A1. E is 1 for A0 bar, B0 bar plus A1, A0, B0. So this is the output for E, and G is 1 for A0, B0 bar. G is 1 for A0, B0 bar. B0 bar is expressed in terms of a NOT gate. Now if we see the 2-bit magnitude comparator. So previously we have seen the 1-bit magnitude comparator. So the logic for a 2-bit magnitude comparator, we have to consider 2-bit numbers. A is, this time the numbers are 2-bit. A is A1, A0 and B is B1, B0. So if A1 is 1 and B1 is 0, then obviously A greater than B because 1 greater than 0. Or here we are basically considering different logic. Okay, and if A1 and B1 coincide, that means if A0 1 and B0 0, then A greater than B because 1 is greater than 0. So what will be the logic expression? This will, for the greater than, if A greater than B, what will be the logic expression for that? This is A0 is 1, so A0 into A0 1 and B0 0. Okay, A0 1 and B0 0, and A1 and B1 coincide. If A1 and B1 are coinciding, that means A1 and B1 are equal, right? So for that, what will be my logic expression? For that, the logic expression will be A1, B1 bar. When A1 is 1, B1 is 0. Okay, and plus A1 XNOR B1. Okay, when they are coinciding, this logic is for A1 and B1 coinciding, multiplied by A0, B0 bar. A0 is 1, B0 bar. A0 is 1, B0 is 0. Now if A1 0 and B1 1, then obviously 0 less than 1, so A less than B. If A1 B1 coincide and A0 A1 B1 coincide, mean whenever you are finding this coincide term, just close your eyes and write the NOR operation, XNOR operation here. A1 XNOR operation between A1 and B1, and means we have to perform the dot operation. And A0 0 B0 1, A0 0 means A0 bar into B0, then A less than B. Okay, and also it is possible if A1 is 0 and B1 is 1, in that case also A less than B, right? So we have to write this logic for A less than B. If A1 and B1 coincide and if A0 and B0 coincide, then A equals to B. So what will be my logic expression for that? A1 B1 coincide means A1 XNOR B1, A0 B0 coincide means A0 XNOR B0. Now for each logic we have to perform this operation. We have to draw the logic diagram. You just write all these input combinations. Okay, A1. So for A greater than B, what we have to do for A greater than B? A1 B1 bar. This is A1 B1 bar, the AND operation between them. Then the XNOR operation between A1 and B1. Then this is the XNOR operation between A1 and B1. Then again A0 and B0 bar. This is A0 and B0 bar. So all these we have to give to a OR gate. So this will give you the output for the first logic. Similarly, for the this is greater than logic. For the equal logic, what we have, for the equality logic, we have the XNOR operation between A nor B nor and XNOR operation between A0 B0, then we have to give it to a AND gate. So this gives us the equality output. And for less than, what we have, A1 and B1, we have to perform the XNOR operation, and then it should be multiplied by A0 bar B0. So this will go to the AND gate, and then here we have this A1 bar and B1. So this is another AND gate. Both we have to perform this OR operation. So this will give us the A less than B logic output.